Yeah, so welcome to the plane curves class today. So we were about to still discuss affine curves and their some local properties of multiplicities at points and smoothness. And just to recall the things that we did at the end, namely this notion of multiplicity at a point. So we said if f is a curve, then first of all we defined a multiplicity at the origin, so m0 of f, multiplicity of the curve at the point. Was the degree of the lowest monomial in f. That occurs there. And we define that for an arbitrary point. So mp of f, this multiplicity is then defined by a coordinate shift in a similar way. So you shift the point p to the origin and then apply the above. So defined by coordinate translation. The multiplicity of the kind is positive if and only if the point lies on f at all. And like the case 1 had a special meaning, namely that we called a smooth point. So we said p in f is a smooth point of f if and only if this multiplicity is 1. So if mp of f is 1, so that had a geometric meaning, namely it looks smooth in the sense that it doesn't have any corners. So if you draw it over the real numbers, some interpretations of that geometrically here, like in a couple of minutes. And we had a criterion for that, actually, namely this Jacobi criterion. So that said this is equivalent to the partial derivatives not both being 0 at this point. So either this or the partial derivative with respect to y at the point p is non-zero. This was the Jacobi criterion, and that helps actually to compute the smoothness in all points simultaneously, just by computing this one derivative or these two derivatives, so you don't have to shift to any arbitrary point and then apply the computation. So there's one more result that I want to give here at the end of this chapter, actually, and then give some geometric interpretation of that. So that is the proposition. I had this already, I think, on the board, is that smoothness has one implication, namely that you can compare ideals using these intersection multiplicities. So the intersection multiplicities were somehow nice numbers. I mean, first of all, they are numbers, so that's nicer structure, easier to compare than just ideals. And that's why this helps. So it is about comparing ideals using or by intersection multiplicities. So the situation is as follows. So we say we have a smooth curve, let f be a smooth point, let f be a curve, and p and f a smooth point. And then we have two more curves, g and h, so that they don't share a common component with f. So let g and h be two more curves not having a common component with f at this point. So in particular, the intersection multiplicity with f will be finite at this point, not having a common component with f through p. So the statement is then that if you consider the ideals generated by this f, so by the smooth curve and one of the polynomials, and you compare it to the ideal with the same curve and the other polynomial in the local ring OP, then so checking this containment of ideals would usually be hard. At least one would need an algorithm to do that. And in the case that this f is smooth at this point, there's a very simple way to do this. Namely, we just have to compute the intersection multiplicity, so that we can do and compare that of the two curves. Namely, this is the case if and only if the intersection multiplicity, so the mu p of fg is greater or equal to mu p of fh. And In particular, of course, you can apply this both ways, and that says that you have an equality of ideals if and only if the multiplicities are the same. In particular, these numbers are finite if there's no common component, so there's no problem of comparing infinity or something. So in particular, we have fg, the ideal is equal to fh in OP if and only if those multiplicities are the same. So we'll first prove this, and then I can say, how you can interpret this geometrically. It's something that we can actually nicely understand in terms of geometry. Right, but let's first prove that. And one direction is in fact simple. So let's start with that so that we have this, that we are done with that. Namely, the left-hand side somehow looks stronger, right? So a statement, a containment of an ideal is like a stronger statement than just a comparison of numbers, and hence like the direction from left to right is in fact easy. Namely, this multiplicity was defined to be the dimension of the local ring modulo this ideal, and if this ideal is smaller, then of course the quotient will be bigger, and hence the intersection multiplicity is bigger. Right? So that is just under the assumption that you have this containment of ideals. Here P of Fg will be the dimension of OP mod Fg, and now Fg is contained in that, so this dimension is greater than or equal to that if I replace that ideal by the bigger one, so Fh, which is mu Pfh. Right? So that's very simple. So as I said, so this looks like the weaker statement on the right-hand side. So the nice thing where we have to do some work and where we actually need the smoothness is the other way around. And we'll use the smoothness so that we first of all pick another curve. We could take a line, for example, but it really doesn't matter, which does not have the same tangent to f. So let's just take a line for simplicity. So say let L be a line through P. That is not the tangent. So it's not TPF. And so we had seen that the intersection multiplicity of two curves is 1 if and only if they are both smooth at the point and have different tangents. So that means if f is smooth at the point, and L, of course, as a line is also smooth at the point, and they're not the same line, that means the intersection multiplicity will be 1. So that's what we will need about this. So mu P of f L is 1. And of course, that means if you take the intersection multiplicity mu P of f with some power of L, which will occur in a minute, then this, of course, will be n by the additivity of the multiplicity. Okay? So that's one setup that we have. What we want to do now to compare these ideals is, well, somehow we're coming from the right, so we just have this, and we want to go to there. And for that, we want to compare, first of all, this ideal Fg with another ideal where we put a power of L in there. So let's consider, somehow say let n be the maximum number, so the maximum natural number, such that the ideal Fg is contained in the ideal of f and L to the n. So everything will be in OP here. And so just quickly to make sure that this exists, well, first of all, of course, if n is equal to 0, then this will be the unit ideal, and this is clearly contained in there. So for n equals 0, that will be true. Otherwise, by what we've already shown, namely the direction from here to there, this containment of ideals will require that the intersection multiplicity of f and g is greater than or equal to n, because here it's n, and that means that n has to be less than or equal to the intersection multiplicity. So there will clearly be a bound on n, so that this happens. So it's just right here, so this exists. So such a maximum, because we are taking a maximum first of all over a non-empty set, in the for n equals 0, we have that Fg is clearly contained in F and L to the 0, since this is all of OP, so this is okay. And also, if we have this Fg in FLN, this requires that n, which was the intersection multiplicity, mu p of FLN, is less than or equal to mu p Fg. So that means there will be an upper bound, and hence there's a maximum of these numbers. When I claim that for this n, we actually have equality. It's not just the containment. All the claim, first step here in the proof, and then, in fact, we have that the ideal of f and g is equal to the ideal of f and L to the n, and not just contained in there. So what this means, of course, is that so that the other containment works as well, that L to the n is in the ideal of f and g. So, i.e. L to the n is contained in the ideal of f and g. So that's the claim, so that we actually have equality. So why is that? Well, let's first of all use the other containment that we have. So for the proof of the claim is we know that Fg is contained in FL to the n this way. And this means that G is contained in that, right? So that inclusion works. So that means G is in F and L to the n, which means that we can write G as some combination of that. So there will be some AF plus B L to the n for some A and B in the local ring. So that works, it works this way, and we would like to reverse that and solve it for L to the n, right? So if we can just rewrite this as L to the n is something in terms of F and G, we will be done, because that's that thing. And obviously L to the n would be G minus AF over B. So what we have to check is that B is invertible, right? Then it works, right? If B is invertible, we can solve it for L to the n, and we have the other inclusion as well. So which elements are invertible? So invertible is every function that's non-zero at the point. So we have to check that B is non-zero at the point, and that's the next step. So now, in fact, B at the point P is non-zero. And why is that? Because since otherwise, if B of P was equal to 0, then it would be in the ideal of the point. Because otherwise, B would be in the ideal. We call this IP. So these for all the functions vanishing at the point. And this ideal we had seen already is generated by any two elements that have intersection multiplicity 1 there. So there was another equivalent statement of intersection multiplicity 1, that the ideal that they generate in the local ring is just this IP. And we have two of them in the F and L. So that is the ideal generated by F and L. And, well, that of course means that we could write B as CF plus DL for some C and D in the local ring, which we could plug in there and get that G is AF plus that thing, so CF plus DL, L to the n, and that actually sits in F and L to the n plus 1. And that's a contradiction to this maximality, right? So that would mean that Fg would actually also be contained in F and L to the n plus 1. And so that's a contradiction to n being maximal. And then the rest just goes through, right? So that means hence B of P is not equal to 0. So that means it in the local ring is invertible, meaning that we could just do that in this equation and obtain that L to the n is 1 over B times G minus AF, and that's an Fg. And that shows the claim up here. So we actually do have an equality there. And of course, now if that's the same, so n is just the intersection multiplicity of these two things. So it's that intersection multiplicity. So let me just replace that here. So that this means that Fg, that's just the claim, is the same as the ideal of f with L to the n. And let me just replace n by what it is, namely the intersection multiplicity. So mu p of Fg. And now the point is we just do the same for h. Right? So we just didn't use h at all so far, but we have everything is symmetric here. So in the same way, we would get that fh is f, the ideal L to the mu p fh. And now, coming from the right, that means if mu p of fh is less than or equal to that, then, so if this number is bigger, then this means that this ideal lies in that, right? So that's just a multiple of that. So it means we have the corresponding thing in here, right? So the inclusion mu p fg is in that because that's the bigger number than that. So that will be in here. That's the end of the proof, right? So, two things about that. So first of all, maybe just, if I have the assumption in there that f is smooth, then we should see an example that this is really necessary. We used it in the proof, but it is really required. Otherwise, it would be false in general. And one example showing that would be, you could take pretty much any example, I guess. So one of the simplest would be, for example, for like, it's again, so the smoothness of f is important here. So let's take something that's not smooth. For example, f is x squared minus y squared. That would be just like the union of two x's, right? Not x's, but diagonals. So that's x plus y, x minus y. That's this thing. That obviously has multiplicity 2 at the origin because the leading term is the power of 2. So this would be singular with m0 of f is 2. So if we take this for f and for g and h, actually just the coordinates. So g is y, g is x, h is y. Then the intersection multiplicity of f with g and h by symmetry is the same. Actually, it's just 2 because, well, this together with x would be xy squared, and that has multiplicity 2. So we have mu p fg is mu p of x squared minus y squared, and g is x. So you could just use that to eliminate the x squared altogether with our rules how to manipulate that. So that would be y squared x, which is twice the number for y, x, which is 1. So that would be 2. And of course, by symmetry, we're the same for f and h. So these numbers would be the same. But the ideals are not the same, because if we take the ideal of f and g, then that's the ideal. We just computed that essentially. So that's x squared minus y squared x, which is x and y squared. And if I do the same for f and h, I get the other symmetry thing. So that would be x squared y. And these ideals would not be the same, right? So they have the same dimension if you take OP modulo that thing, but they are not the same ideal. Otherwise x would have to lie in there, then it would be xy, which has multiplicity 1, and it hasn't. So that would be an example that it's really important. So for these things, so if this is f, and gh would be, of course, the two axes. G is X, so that is G, this is H, that would just be false, right? So you couldn't compare those ideals just by comparing the number. But for a smooth F, it's okay. So that we've just shown. And there's, as I just promised, like three things I want to say about geometry for these smooth points in general. And the first is not even related to the proposition here, but to the Jacobi criterion before, and probably you noticed already that the condition in the Jacobi criterion, namely that the derivatives, at least one partial derivative, doesn't vanish, is if we are over the real numbers, like where we can draw pictures and so, and actually also over the complex numbers, if you knew enough complex analysis to do that, is exactly the condition that we would need for the implicit function theorem to hold of analysis, right? Which tells you that locally at the point you could solve the equation of the curve for this variable, for one of the variables, in terms of a differentiable function, which means that the graph of the curve is the graph of a differentiable function, which is the same as saying like it doesn't have any corners. I mean, it's a differentiable function. So just a remark about geometric interpretation. For the ground field of the real numbers, or say, or the complex numbers, but for the complex numbers, you would need the corresponding result for complex analysis, which you might not know. I guess for the real numbers, you probably know, but for the complex, it does hold as well, but probably you haven't seen it. As A, so the Jacobi criterion, namely that the f by dx at the point and the f by dy at the point is not equal to 0, 0, just states that the implicit function theorem is applicable. At this point. Which would mean that, I mean, in whatever your wording is in that case, that means essentially that f is the graph of a differentiable function, either x in terms of y or y in terms of x. Or sometimes you'd say it's a one-dimensional manifold, it's the same thing, just a different word. Also just, and in any case, it both means it doesn't, if you draw it, it doesn't have any corners, right? It's a smooth thing. We just put this in quotes, so f has no corners or anything else. It looks locally like a real line. Say like a bent real line, right? So it must look something like this, locally around the point P. So in that sense, you can clearly understand where this Jacobi criterion comes from and why this should hold. So that's about the first proposition, like the Jacobi criterion that we had before. As I said, maybe you noticed that already when we did that. This proposition here that we just had is maybe a little bit harder to interpret, and you can in fact do this either using analysis or using algebra, depending on what you like better and what you maybe have seen before. For a second, so regarding the proposition that we just had. So note that what we had in the proposition, namely Fg, well, either containment or equality in OP, is equivalent to saying that if you mod out this f in OP, you just have a containment of ideals generated by one element, and this would just be the same by standard algebra saying that the ideal G is contained in the H in OP mod F, right? That's exactly the same thing. And this OP mod F actually has an interpretation, because OP was local functions in the plane around the point. And if we mod out F, right, so F is a function that's identically 0 on the curve. And that means if we mod that out, that corresponds exactly to functions on the curve only. So that's one standard way. I mean, I don't want to really prove all that. It's just a remark, just in geometric interpretation, right? So that corresponds to functions on the curve. Right, we'll have this later in class again in a couple of weeks, because a function on the curve should be a function on the ambient space, but we identify two functions if they are just the same on the curve, and that's what we are doing here. Now, if the curve, and now there's some of the way that splits, now we can think either analysis or algebra. If we think analysis, then we had just seen that the curve should be a one-dimensional manifold. Okay? And that it's a one-dimensional manifold, it locally looks like the real numbers. Means that it should behave like the real numbers, right? So you can consider a coordinate z on F. So here's the point P. Consider this as a real line. And a nice function, say at least an analytic function, and everything here will be analytic, it's quotients of polynomials, should be expressible in terms of this one coordinate z only, and should be a function in this one variable. So hence, in OP of F, G is an analytic function in the variable z on F. So it's like an analytic coordinate on F. And hence we should be able to write it, I mean, just factor out the multiplicity, right? So it's just a function in one variable. So that means G somehow corresponds to something like A times, so let's do it such that P is the 0 point again. So that's probably easier. Then we would write it as A times Z to the K, where A is a function, this is non-zero at 0. And this is the order of the 0. Of G at P. And so if it's just a function of one variable, you should be able to write it that way. And the same way you do it for H. So in the same way, H should correspond to B times Z to the L, where L is the order there. And we had seen that this order is just the multiplicity. So that we should be able to interpret as mu P of Fg. And that we should be able to interpret as mu P FH. And then we see, of course, that, I mean, so these are all units. Again, it's pretty much the same argument as we just had. And so we will have which way around. So this ideal lies in that ideal, if and only if this is the smaller number. So if L is less than or equal to K, because then this is the divisor of that. And you get exactly the same statement because these are the multiplicities. Hence, we expect that G is contained in H in OP mod F, which is the same as the statement in the proposition, if and only if we have the numbers the other way around. So that means K is greater than or equal to L, which means the mu P FG is greater than or equal to mu P FH. So that's the analytic idea behind that, and that obviously requires sort of that we can think of F as locally just a real line with one coordinate. And if it's not a smooth curve at the point, like if it looks at that, that just breaks down, and then this doesn't work. So that's the analytic picture. And the algebraic picture is probably only applicable if you had been in a commutative algebra class before. So if not, just ignore like the next 3 minutes or so. So if you had been in a commutative algebra class before, maybe you had seen this motivation already in a different context. Namely, in commutative algebra, this ring here, OP mod F, will be a discrete valuation ring. And right, so you could either, I mean, if you were in such a class, you probably have means to prove that. Like it's a two-dimensional polynomial ring, you mod out one function, so it's a one-dimensional thing, and then it's local, and then it's the DVR. And that, on such a discrete valuation ring, you do have a valuation function, and you know that the ideals, you can explicitly classify the ideals. Namely, you have a generator of the maximal ideal, which would be Z here, or the IP there in the proof. And then all the ideals, the non-trivial ones that exist there, are just generated by the powers of that, which in particular means that you could compare two ideals just by comparing the powers, and the powers are just the K and L there. So and that's pretty much the same argument as that, actually. So like if I had to give like a commutative algebra class and explain DVRs, I would probably draw pictures like that and explain it analytically in that way. But if you have a different way of thinking of DVRs, then it would be fine, but you would arrive at the same result. Right? So algebraically, or like with the same idea, S and B, OP mod F is algebraically a so-called discrete valuation ring. So as I said, if you don't know what this means, then just ignore that. But if you know it, then you would know that this does have a valuation, and you can use the valuation to compare the ideals, and that's precisely the statement we prove. And for it to be a DVR, you actually need a smoothness condition. So maybe in commutative algebra, we didn't call it smoothness, but you want a regular ring or whatever is the corresponding notion. So, i.e., it has a valuation that can be used to compare ideals. So let me not be more specific about that. I mean, it's not the topic of this class, but if you had seen this, then that would make sense to you, and if not, just ignore that. So we have our proof here, and we have also an analytic interpretation, which is probably nice, and that's what we want. Right. Yes, any questions about this? So if not, that was like in the chapter on intersection multiplicities. So like to study local, how curves intersect. And before we actually continue now with the general like theory of curves, what we can do with them, there's one step that we have to take, namely to pass from from our affine curve to projective curves. And it's somehow, the earlier we do this, the better, because it's sort of a generalization of curves, of our affine curves. And if we do this later, then we have to repeat all the stuff that we had done before and see that it works for the projective curves as well. So we just introduce it as early as possible. So that's the third chapter here about projective curves. And let me first say, what is the idea about that? So one central question that we will study like in a week or 2 weeks time about is, which is, I guess, pretty much a natural question, in how many points curves intersect. So if we have two curves, f and g, let's first start with the motivation. Say, given two curves f and g, how many intersection points do they have? So how many points are there in f intersect g? So that will be a question that we would be able to answer like in 2-3 weeks time or so about. So and that of course corresponds to pretty much the case that, you know, if we had only one polynomial in one variable instead of two polynomials in two variables, and I would ask you like how many zeros has a polynomial in one variable, and you would of course say, well, whatever the degree is, right? So you have to count the zeros with multiplicities, and if d is the degree, then you get d zeros, at least if we're algebraically closed, and if we're not, we get at most d zeros. So we want to have a similar statement like that. And there's one problem with that. Well, maybe it's not really a problem, but something that it's more of an annoyance, I would say. Namely that even in the simplest case of two lines, I mean, it would be the simplest case you could think of, like you have f and g are both a line, you would expect them to intersect in a point, in one point, exactly one point. But even if the lines are not the same, there's the possibility that the two lines are just parallel and don't intersect in any point. So somehow a problem. So even for FG line, for lines, and say distinct lines, so of course if they are the same, I mean there's nothing to count to say distinct lines. There are two possibilities, namely they could be parallel. So one is just the shift of the other, so you could have like f and g. And then we have no point in f intersect g, or they could not, right? So if it's like that, then of course in any other case you would have exactly one point in f intersect g. And so as I said, it's not really a problem, but it would of course be nicer if we didn't have this distinction. And for that, there's actually a way around this, namely to add points at infinity. So consider not just the plane A2, but a compactified version that has points at infinity. And so that these curves do intersect at these points at infinity. I mean, it's something that you could imagine, like the two parallel lines meet at infinity, sort of. Just the point is, of course, so that the problem doesn't get even worse. Of course, these two lines should not meet at infinity, because otherwise they would have two intersection points and we had we wouldn't have gained anything. So we do not want, in case you had seen that, a compactification by saying we just add a point at infinity. Like, so there's in topology like a construction how you could make any space compact by adding a point at infinity, putting a suitable topology on that. That's not what helps there. And because that just would make the numbers 0, 1 into 1, 2, and there would be no gain. So what we need is a compactification that still sees whether these lines go in the same direction. I mean, the same way as intuitively you would say two parallel lines meet at infinity, but like two lines like that do not. So that's the idea. And the idea is add points at infinity. So that we could say, so this meets here at infinity. That would be this point here. But not just one, but one for every direction that you could have, right? So that means if two lines have the same direction, they would meet. And if they don't have the same direction, then they don't. So we add point at infinity, namely one for every direction. Where direction also means, of course, if you see the real pictures here, that like going to the left and going to the right should be the same, right? So you don't want to compactify either the real line by saying we have a minus infinity and a plus infinity, because then the lines would again meet in 2 points. That's bad. Don't want that, right? So that point should be the same actually as that one. So direction means it doesn't see left or right. And so that's the idea. And that's in fact what projective spaces and projective curves do. They just extend the affine space A2 to a projective space P2. Actually, we could do this, make this in general for any dimension, but then, of course, afterwards restrict to the plane, the 2 coordinates, and doing this addition of points. The question is how to do that. And again, just a remark, is the idea to construct this. So this compactification of AN is the following. we want to embed the affine space. So first of all, embed an in a vector space of dimension 1 bigger, kn plus 1, by sending a point x1, xn, so this would be the coordinates here, to 1, x1, xn, and consider the line through the origin in kn plus 1 and this point. So consider the line in kn plus 1 through 0 and 1, x1 up to xn. So that means we have a one-dimensional linear subspace, and it's a line through the origin and this point. So the picture does look as follows. So you could start with a, well, we have A2 here, and a certain point, say x or x1 up to xn. And we embed this in the space of dimension 1 bigger. So usually we will take another coordinate which we prepend to the others and call it x0 to keep the names of the others. So here we have x1 and x2. And the zeroth coordinate here, so that we usually call x0, we set to 1. And that means we just embed this. So what this map does is we just embed the plane up here, right, in the at the height 1. So to say, if x0 gives the height, then there will be height 1. So that's our image of A2. And what this map does here is that we take a point now, so I don't have any yellow yet, so if we have a point here, we take the corresponding image point, which would be 1, x1, xn, and then consider the line through the origin, so that thing here, in a vector space of dimension 1 bigger. And that's obviously like an injective map, right? So if I have two different points here in A2, I would get two different lines. That is the idea, and in fact, in a minute, we will define our projective space to be the set of lines through the origin in a vector space. Just one remark before that: why does that construction do what we want here, namely to add points at infinity? Well, what you could see actually is if I take the same picture, I'm not sure I want to draw it in the same picture, but yeah, I could. So if we consider this point moving off to infinity, so let me take a different color at least. So consider, for example, a sequence of points going to infinity here in the plane. What that would correspond to is here, so you get the same sequence of points here, but we rather consider these lines here through the origin, like this. That means the slope of these lines will become smaller and smaller. These are lines, they all lie in a plane. So if these ones are on a line, so it may be hard to just imagine this three-dimensional space. So they will be in a plane and have smaller and smaller slope. And the limit point, which does not exist here in the picture on the left, would here on the right be a line that is just entirely in the x1, x2 plane. Right, so you could really want to say that these lines have a limit line, so which would be that one, which lies in the x1, x2 plane. That means it does not intersect that thing, so it doesn't correspond to any point in here, but that would be our point at infinity where the things meet. And you would clearly see that if you have a different direction here for these points, if you go off to that direction, then you would get a different limit line in the x1, x2 plane. So that is the idea of the construction of projective space. And that I think we can then define now with that idea. So definition is, so we define for a natural number, projective n space, which we would write as Pn, or again, this is over a field, so you could either write Pn or Pn over k as the set. So again, at the moment it doesn't have any structure but a set, as the set of one-dimensional linear subspaces of a vector space of dimension 1 bigger, so k to the n plus 1. That's the definition, right? And that's the picture here on the right. And I think so the picture should tell you a little bit why this makes sense and why we do it that way. So if we want to work with that, if we want to compute that, so then the notation, well, the elements would be one-dimensional subspaces, and that means they are all spanned by a non-zero vector, which is defined up to a common scalar, of course, right? So that means that, I mean, you could take any point on the line would be a generator. So any such line or any such one-dimensional linear subspace is determined by a spanning vector which I call then now x0 up to xn, because we have one more coordinate, which is of course non-zero. It should span a one-dimensional subspace, so it's not equal to 0. And it's well defined, well, it's unique up to multiplication by a scalar. By a scalar which is not 0, right? So by some lambda which is in k, but not 0. And that gives you another way of defining that. So hence, there's a different way to describe Pn, and some people also would take that as a definition. It's like directly equivalent. And you could say Pn is the set of such vectors without the 0 vector. And then you mod out an equivalence relation where the equivalence relation is just multiplication by scalars. So with x0, xn equivalent to x0 prime up to xn prime, if and only if there's a lambda in k star, okay, without 0, such that xi prime is lambda xi for all I. And so one of the vectors is just a multiple of the other. So that's just a different way. It's directly equivalent to that definition. But that gives us a way to deal with these things. Then we have coordinates on that space. So x0 up to xn. They are just not really uniquely defined. They are only uniquely defined up to scalars. And so first of all, the notation for that, for the equivalence class, there's a standard notation, namely you put, instead of the commas, you put colons. So first of all, so we write, sorry, notation. You write x0 and then colon up to xn for the equivalence class. Of x0 comma up to xn. That means in this notation, so whenever you write this colon notation, that would mean not all numbers are 0. So that's the condition here, and they are defined only up to a common scalar. And obviously the colon notation is just somehow to remind you of that it's only the fraction of two coordinates which is invariant. So if you take any, say if you take an x1 over x2 or an xi over xj, then the lambda drops out. So that would be well defined. And hence you write this as if this was a division, sort of, right? So you have all the quotients of any two of the coordinates. These coordinates x0 up to xn are then usually called either projective coordinates or homogeneous coordinates. So they will be related to homogeneous polynomials later on. That's where this name comes from. So we call x0 up to xn in this notation the projective or homogeneous coordinates of the point So of this point, x0 up to xn, which means, i.e., they are not all 0, like the 0 point doesn't exist, and unique up to scalar multiplication. And that gives us a way to actually compute with that name. So we have coordinates on that space. Just there's one more coordinate, but to compensate for that, we have just only the quotients that are relevant. So that's notation. We can actually, just as a remark, again, have some more geometric interpretation of that thing. Maybe there's two ways we should think of that. So the geometric interpretation of the whole thing. Interpretation. Now, say, well, I mean, what about geometric interpretation? When we have one here, right? So what do we want to interpret more than that? The point is that we will get confused. You will get, at least I will get confused, if we constantly try to think of points as lines. And I mean, as we defined it here, a point in projective space is a line in a vector space. And then if we identify a point with a line, this would be, I mean, that's not what we want to think of this, right? For example, like in a couple of minutes, we will consider curves over that thing. And the curve should consist of points, but now the curve would consist of lines. It would be a family of lines. It's just weird, right? So you don't want to think of it that way. So you really want a picture where the points are actually points. And that you can do in two possible ways, and both are somehow important. Namely, the first thing we've already seen here, namely the affine an, or here, I mean, it was the plane, but in general, an, of course, sits in Pn by this mat up there. So, say there is, by construction, pretty much as we did there in the beginning, there's an embedding from an to Pn by sending a point x1 up to xn to 1 and then colon x1 up to xn, and that's exactly what we did in the picture up there. And so sometimes, so the image of that consists obviously of all points here where the first coordinate is non-zero. I mean, you could rescale the first coordinate. They're only well defined up to a common scalar, but you could not make it 0. So that means with image, let's give it a name. So we call this U0 usually. And that is just the set of all x0 up to xn in Pn such that x0 is not equal to 0. And in fact, we often want to use this embedding to identify an as a subset of Pn. So we'll use this to identify an. Of Pn, and then, so in the same way as we thought of it in here, so it should be a compactification. In particular, it should contain the original space an, and it does in that way, so namely by identifying an with this U0. And the points that are not of this form are obviously the ones that have a 0 in the first coordinate here, right? So the complement is the set of all points x0, or let me just write this that, so I will just have a 0 here, x1 up to xn. And that, of course, by definition, is just a projective space again, right? Just of dimension 1 smaller. When you just have restricted the first coordinate to be 0. So that is, you can think of this as a Pn minus 1, because you lost one coordinate, but you still consider them up to scalars, and they are still not supposed to be all 0. And this Pn minus 1, just recall, I mean, this Pn minus 1 was, by construction, the space of direction vectors in an, in Kn. And so these are precisely the points at infinity, namely one in each direction. So you can see this pretty much directly from this description here. So this you would call, let me just go on the board. this would be the points at infinity. These are the ones where like the zeroth coordinate, or the one you write first, is 0. So hence, in this notation, we could write that Pn is a disjoint union of An with Pn minus 1. So here we have a disjoint union. And so that would be somehow the An part. So usually call this the affine part. And the coordinates x1 up to xn you would call like the affine or inhomogeneous coordinates. And these would be somehow the points at infinity. Namely, as we can see from the definition, we have one for every direction, and that's precisely what we wanted. For every direction in An. And that shows us this way of how we add points at infinity. That's one way to think about that. So we have and that corresponds to our first motivation. Then we have an affine space, we add points at infinity, namely one in each direction. That's exactly this. The second way to interpret that is, which is often algebraically nicer, is that, of course, this sort of breaks the symmetry among the coordinates. Then we have n plus 1 coordinates, but we say that there is a distinguished zeroth coordinate, and that tells us whether we are at infinity or not. But of course, the definition here is totally symmetric in all coordinates. And so from an algebraic point of view, it's often nicer to say, well, I mean, we could take this embedding here in that way, not just putting the first coordinate to 1, like the zeroth coordinate to 1. We could also do it with any other thing. And that means we could define not just this u0, but also uk, where the kth coordinate is not equal to 0. And it would have the same properties. It's just given by renaming the coordinate. It has the exact same properties. But the point is that if you take all these UKs together, then they would cover the whole projective space, because not all the numbers can be 0 in projective space, right? So you would get the cover of Pn by spaces that all look like the affine space here, that are same as one of the U0s. And that's the second way to think about that. So B says you could also say we could define similarly a UK, which would be x0 up to xn such that xk is not equal to 0, or k from 0 to n, not just for 0. And then we have, so then each UK looks like an affine space. So looks like it's a bit vague. I would want to say it's isomorphic, and it sort of is, but we don't have the right category to talk about this. So we'll just say it looks like an affine space as above. And that's now here the important point. Now we would say that our Pn is the union of u0 up to un. So that means, as it cannot happen that all coordinates are 0. And so that means that Pn is covered by affine spaces, namely by n plus 1 affine spaces. By n plus 1 affine spaces. So if you want to retain the complete symmetry among all the coordinates, then you could do it that way as well. And we will in fact do both. I mean, sometimes the one thing is more convenient and sometimes the other is more convenient. So if you know this wording, I mean, then this would sort of tell you that over the real numbers, for example, the Pn would be an n-dimensional manifold. So if you've heard that name, it's somehow a space that can be covered by n-dimensional thing that looks like R to the n locally, and that's precisely the case. So if you're about to draw a picture of that Pn, you would draw something that locally looks like Pn at every point, r to the n at every point. In fact, it's covered by r to the n. Yeah, we can, in fact, to get a better picture of that, maybe you've seen it in other classes as well already, say in topology or somewhere else. See what these pictures look like if you want to draw it. So, for example, the first example would probably be if we take P1. P0 is boring, but P1 is already probably the first interesting case. So P1, we would write. Let's take the first one here, like the geometric interpretation A. You would write it as A1 union P0. And so that's just an affine line. And P0 in P1 would be the point of the form 0x1, where x1 has to be non-zero. And that's, of course, all the same point, right? Because they're all multiples of each other. And so that is just one point. And as we've added points at infinity, it makes sense maybe to define this or write this point just as one point infinity. And hence our P1, we could write this as A1 union infinity. So the P1 is somehow the simplest case that just adds one point, and you can think of it as one point at infinity. And if you do that construction, say for the real numbers, it would be, or the complex numbers, it would be really the same as like a one-point compactification, as you might have seen in topology. Yeah, maybe let's draw some topological pictures. Well, say what are the topological properties of Pn, and that of course means that we have to go to the real or complex numbers over R respectively C, because then we can draw pictures. That's always nice. And so what does it look like over the reals over the complex numbers? So the one thing that we can note there is that as we have this equivalence relation, right? So we can rescale any point in Pn without changing the point. That means over R over C, that every point in Pn has a representative by a unit vector, right? We can just norm it, divide it by its norm, and it's still the same point. So that means then every point, and that is true both for R or C, doesn't matter. So every point in Pn, because of the rescaling, has a unit representative so x0 up to xn, so unit now not in the algebraic but in the analytic sense, so i.e. with the sum of the absolute values squared equal to 1. And that here in the dimension of one space bigger is of course a compact space. And that means that Pn is the image of a compact space. It's just a unit ball, like no matter if it's like the complex or the real numbers. And so that means it's the image of a compact ball here, I should say, not the interior, but on the ball. And images of compact spaces are compact range, and so that means there will be compact spaces. So this is a compact sphere. And hence that means that Pn are, and also over the complex numbers, are compact spaces, topological spaces. Yeah, over R and C, just like that. Okay, as images of compact space. We can actually, for small values of n, also draw explicit pictures, and somehow the real case is maybe even the topologically even more interesting one. So what can we say about the reals? We still have this equivalence relation that we can multiply with a scalar without changing the point in Pn. And you could use that, for example, to make every point in real projective space to be represented by one where the 0th coordinate, say, like the first you write down, has a non-negative number, right? So you could restrict to x0 is greater or equal to 0, because you could always multiply by -1. So moreover, A, if we are over the real numbers, then every point in Pn has a representative, so x0 up to xn with x0 greater or equal to 0 just by multiplying it with -1, which is allowed. And it is in fact unique, right? Unless x0 is 0. So if the vector here has really a non-zero value, there's even a unique representative of that. If we still are in the unit picture here, has a representative, a unit representative, meaning that it's again the same as that, i.e. with norm 1. So that means over the reals you could still take like the -1 to let it put in the upper hemisphere. So that means we obtain, first of all, the upper hemisphere, which means that we get all x0 up to xn, or I call this x, in r to the n plus 1, such that the norm of x, meaning like the Euclidean norms, and put the 2 norm, is equal to 1, and x0 is greater than equal to 0. And as I said, so the unit representative with the first positive non-negative entry is unique, except the first number is 0. And then we get, of course, we can still multiply it with -1. It just doesn't change anything here. It would put like the other numbers just to their negatives. And that means the space is not quite the upper hemisphere topologically, but it's the upper hemisphere together with an identification, namely at its border, so where x0 is equal to 0, we still have to identify opposite points. With opposite points identified. On the border or boundary, x0 equals 0. And so that is something you could actually draw. So for example, if we take n equals 1, then we take in R2 the upper hemisphere, which is that. And you have 2 points on the boundary, and you have to identify those 2. So now we identify this. And that means you get just a circle, where this is the one point that comes from here. That was in the example before what we called the point at infinity. And here is the real line, and we still get the picture that P1 is the affine line plus a point at infinity. For n equals 2, it's harder to draw, but it's still the same thing. So we would have to take the upper hemisphere, which is the upper part of an ordinary sphere, like of a 2-dimensional sphere in 3 space. And then on this boundary here of the thing, we still have to identify opposite points. So that means we take a point here. So if we have 2 opposite points, then we have to identify this. And not just those 2 points, but any 2 points. Right? So I mean, you identify those and on all those points together. And that is actually a space, I mean, you could have a look at maybe a topology class on the internet or something that's not embeddable, in fact, in 3 space. So it's hard to draw a picture about that, of that. So let me just write this. So it's not embeddable. So I have not so easy to draw a picture on that on the board, but you would clearly find pictures if you look for that. So I usually think of that topologically as that way and just say, well, take the upper hemisphere and identify two opposite points. Any two opposite points on the boundary. Then you would get the space. And that's a picture that works in any dimension, right? So if you want Pn, then you just take the upper hemisphere, you probably just can't imagine it in n-dimensional space, and identify opposite points on the boundary. If you try to do that with a sheet of paper, you also fail, right? I mean, of course, the upper hemisphere itself is just topologically like just an ordinary circle. Right? You can take a piece of paper, but then you would have to identify opposite points. I mean, I can do this once, but as soon as I try this with every pair of opposite points, I will fail, right? So I'm not even trying that. So that means that, but these are spaces, I mean, if we're in a topology class, I mean, these are really nice and non-trivial examples. So, I mean, as easy as the definition is, like the topological properties are really quite interesting of these spaces. If we're over the complex numbers, of course, like the thing with the pictures doesn't get much better because, I mean, I would need higher dimensional pictures and I'm not even trying. So the only thing I could do is like the example up there. So if I take P1 over C, it would be the complex line, like A1 over C, together with a point at infinity. So let's just restrict to that. So P1 over C is A1 over C, which is just C itself, together with one point at infinity, which sort of sits at infinity. And there the picture is sort of like you get an actual sphere where, well, somewhere you have the point infinity. And otherwise it's just a sphere. So it's the same as if you, so there the picture, it's not the same as P2 over R. I mean, you might think so, but it's not, because here you really add only one point. So that's as if you take the plane and identify all the boundary points with the same point, so not just two opposite ones. And then you make this into a sphere. Right? So that's the, well, let's just keep it at that. Otherwise it's probably hard to draw pictures about that. Luckily, this is a plane curves class, and we will not ever talk about anything higher than one dimension, even over the complex numbers, and we can still draw pictures, which is nice, I guess. Yeah. So, I have questions maybe up to that. So these are the projective spaces. So maybe, as I say, maybe you've seen them before somewhere else, for example, in a topology class or something, and that will now be our ambient spaces for curves, which are then called projective curves. Okay. So if we want to use that, then the complex projective plane, so P2 as the ambient space for curves, that would mean, of course, that we want to, so that's now the idea, so now use Pn or P2 then for curves as ambient space for varieties or curves. And that means we need to be able, I mean, of course, you want to say again as before that they are zero loci of polynomials or something. Right? And it's, of course, natural then to think of polynomials in these homogeneous coordinates and consider their zero loci and call them projective varieties. The problem with that is that these coordinates are not well defined. Right? So note, so we want to, let me start with like that. We want to define varieties. And then, of course, also curves in a similar way as zero loci of polynomials in the homogeneous coordinates x0 up to xn, but the problem is that these coordinates are not defined uniquely, but only up to scale. So x0 and then r for a point. Are only defined up to scalars. And that means that polynomials would not be functions on that. So if I just consider polynomials in k x0 up to xn, then they don't determine well-defined functions on Pn. I think that's sort of obvious, right? I mean, so if you take the function x0 itself, I mean, that would be a polynomial, and one coordinate is not well defined on a point, so that just doesn't work. But so the point is that you can solve this problem, at least partially, by considering only homogeneous polynomials. That's something that we have to consider next, and that's also why these coordinates are called homogeneous coordinates. Namely, just write down the remark. So starting with that observation here, but if f is a homogeneous polynomial, so i.e., that means we could write f as, I mean, as usual, it's a polynomial, so it's some a i0 up to in, x0 to the i0 up to xn to the in, some finite sum with coefficients a, but you restrict to the ones that have the same degree, so i0 plus up to in equals d for some fixed d. Right, so that would be a homogeneous polynomial of degree d. Then if we do the rescaling that you can do in projective coordinates, then f of lambda x0 up to lambda xn. So if you plug in a lambda here, then you would pull out a lambda to the sum of the exponent, which is exactly d. So that means f of lambda x0 up to lambda xn would be lambda to the d times, and then the same sum as before. Yeah, just call this f, right? So it's f at 0 up to xn, because you pull out the same power of lambda in every term. That still means that f is not a well-defined function on Pn, right? If you rescale, you get a factor, but at least the zero locus would be well-defined. And if you had two polynomials and they are of the same degree and homogeneous, then if you take their quotient, they would also be well-defined, right? Because then the lambda to the d drops out, at least if the denominator is not 0. So there's two observations with that. Hence, so if f is homogeneous, then then for a point P and Pn, say P is x0 up to xn, the value f of P is still not well defined. But the condition that it's 0 is. So that's A. And we will actually then write in the following something like f of P, although it's not well defined, but it will only occur in these equations f of P equals 0. I mean, it looks so natural to write this, so we'll just do that. And although this is not a well-defined thing. So that's part A, and as I just said, part B. So if we have two polynomials and they have the same degree and they're both homogeneous, then in the quotient, if you consider a point of Pn where you can plug in the value, which means the denominator doesn't get 0, then you would actually have a well-defined function. You don't have any problems anymore. And that's the second thing we can do if we have homogeneous polynomials. So B, if f and g are homogeneous of same degree, by d, then the function then f over g is a well-defined function at all points p and Pn with g of p not equal to 0. Right, and that is just, of course, since f of lambda x over g of lambda x would just be lambda to the d f of x over lambda to the d d of x, and then the lambda over d just cancels. That's the same. So that would work. And we'll actually use both. So at the moment, we'll just consider part A here because we just want to define projective curves. There we need 0 loci. So that's part A. But of course, later on, we also want to consider functions. I mean, we will have local rings on projective curves. We have functions on projective curves. And for that, we always have to make sure that we consider quotients of two things that are homogeneous of the same degree. So both remarks are actually important. But for the moment, as I said, we can just use part A to define our projective varieties. So let's just do this in general. So that's the last thing we do here in general, and then we specialize again to curves. So, and that is now entirely analogous to the affine case, together with these modifications that we just said. Namely, we say let S in kx0 up to xn, so now we have one variable more, which we call x0, be a subset of homogeneous polynomials. So they don't all have to have the same degree, but they all have to be homogeneous. So then we set V of S, and that is just the set, the definition is the same as before, it just means something a little different. Namely P of Pn such that f of P equals 0 for all f and s. And so that sits in Pn. It's called a projective variety. And of course, we call this again like the 0 set or the 0 locus of S. As before, we would write if we have like a finite set. So again, of course, we write V of, and then the set of finitely many polynomials as just V of f1 up to, shouldn't use n because n would be the same number, so say fk up to fk, just as before, just as in the affine case. And if we have to distinguish between affine and projective, I mean, just recall, I mean, the subset of homogeneous polynomials is in particular a subset of polynomials. So for that setting, we would also have defined an affine 0 locus in a to the n plus 1. And in fact, one might sometimes consider that. So if we want to make sure that we stress to that we consider the projective 0 locus, I would sometimes write a VP here, so with an index P for projective, and write a VA for an affine 0 locus. But otherwise, I think most of the time it will be clear if we mean VP or VA. But if not, we might distinguish by an index. So sometimes you write the P of F to denote this projective 0 locus. In order to distinguish it from the affine one. And the affine we would write then as VA of the same set. I mean, you could take the same set, but then it would lie in a to the n plus 1 instead of Pn. So we should do both. So these are projective varieties, and as I said, they are like entirely analogous to affine varieties, just that we have somehow now points at infinity, and a lot of the theory is really very much in common. So that's why I said we want to do this at the very beginning. And so now we only have a quite small part, like to check which properties we had so far will carry over from the affine to the projective case. So that's now in question. So like now let's carry over some concepts from the affine to the projective case. That means we are now quickly, I mean, not so quickly that we can do this today, but I mean, take today and then like the first couple of whatever minutes in the next lecture, just go quickly through like chapters 1 and 2 of this class and see what of our stuff that we did hold for projective curves as well. And so the first thing that we did is that we considered the union intersection of these varieties. A remark, first of all, so as in the affine case, we have that if we take V of f and then the union of V of g, we would have V of f times g. That's the same as before, and V of f intersect V of g would be V of f and comma g. So that, for example, is something we had for the affine case for 0 loci of one polynomial, and that holds just in the very same way as in the projective case. Yeah, so because now we want to define curves, and we just have 2 minutes, so maybe let's not push it. But I can already just give the idea. I mean, what was a curve for us? We said, well, I mean, we didn't want to define curves like as V of f, but we wanted to say, well, they are just polynomials modulo scalars. And so far, I think we had seen already that it makes sense because, or that it's just useful to do that because things like intersection multiplicities really want to see multiplicities on components. So, for example, something like the additivity of the intersection multiplicity would not hold if you just forget about components. And so we actually want to do the same here. And hence a projective curve will still be given by one equation in the projective 2 space, but we don't want to define it that way as a V of something. But again, we would say it's a polynomial modulo scalars. However, we just take now a polynomial in 3 variables and up to scalars again, and it has to be homogeneous. Right? So that's the 2 things that we have to change. So we have 1 variable more, but then it's homogeneous. And that will be a projective curve. And then we'll see that many concepts actually that we had so far carry over from the affine to the projective case. So that we can do, I think, next week. So let's just stop here unless there's any questions. Just stop here and consider our projective curves next week. Right? Okay.